highly problematic. There are some methods when you're trying to do skin segmentation, how to avoid this. One of them is just doing some filtering. If you do filtering, as you know, if you use linear filtering or a medium filter or something like that, you will be able to reduce the hairs or even remove them, but it will deform your mold, so it won't be good for segmentation. The other thing that you can do is in painting, but that's a process that can be computational very expensive. So one thing that we can do is analyze the spectrum of hair. Here we took like three samples again. Red one is for a skin sample, blue is a mole, and there are two green ones that are from hair. As you can see, the problem with hair is like depending of like the color, because there are some hairs that are thinner or they're blonde, or some hairs that are thicker and lighter. The thing that you're going to see here is that it can behave. The visual spectrum can be very similar to the color of the skin, or can be very similar to the color of the mold. However, when it's something that we discover as we were working, is that these hairs that are very thick and they are very black, they might be very similar to the hair in this spectrum, but it has a high contrast in the infrared spectrum. So we start to analyze that, and we realized that when you took, for example, at 900 nanometers, for example, in this image, you can see the molds, but you cannot see them for 900 nanometers, but you can see the hair. So if you can using this channel or this part of the spectrum, we can use it to remove the hair in this area. So this is like a very simple proposal. Actually, this is actually something that I did quite recently, because what I did last semester was more ambitious with SVM, trying to do a training segmentation that it didn't work very well. This one it will sound a little basic, but what it is very simple. You just have, you image at 480 nanometers. After you do some, after you transform it because you get the radiance, so you change the radiance to absolute reflectance. So you take your image and this one is in infrared. In some cases, okay, we'll show you this. In some cases, you cannot see the mold in infrared. In some cases, you can see part of the mold, but it doesn't matter because it's actually this liquid work. So what you do is like you just subtract both images, and you get something that has a better contrast. And then you can do just this is like a very simple thresholding method. This is just OXO method. This will be improved work with, for example, with the M-ray method, and then you just do some pre-processing, and that's pretty much it. As you can see, the final result is your segmented mold. However, it's not. I think it's segmented, but it's not completely correct. As you can see here, for example, there is this hole here. Kind of here, it's a little exaggerated. So the idea is like for the next step of this project will be, instead of using this as a final segmentation, is to use these areas that are already here, and we use them as seeds for a region growing segmentation method using another hyperspectral channel. So, the future work is use segmentation using different thresholding methods, using immersion assisted segmentation, and maybe in the future use this for actually extract the features of the segmented area, because the potential of hyperspectral camera is not only the segmentation. Actually, segmentation is not such a big advantage to use hyperspectral. But when you do the feature extraction, when you get the segmented area values, the color values, or stuff like that, it would be very useful to use a hyperspectral camera. Well, to support this is as I told you, it's a very ongoing project. It's still in development. Yeah, that's it. Okay, thank you very much.